Okay, we'll give this a shot. This is a little different than what I'm used to. Namely, I can't actually see on my screen what you see on the projector. So we'll have to get into a cadence to make this work. I assume I'm being recorded. That's kind of a bad idea, but we'll see what happens. This is Postgres Performance and Maintenance. As you see, that's the mammoth. You guys all have the sticker. That's the command prompt mammoth. We're the oldest, at least in North America, we're the oldest Postgres company. We've been around since 1997. This training is Postgres Performance and Maintenance. I cannot see that. I am JD. You've got my email there. Feel free to email me, although I get a lot of it, just like I'm sure the rest of you do. You're probably better off trying to find me on something like LinkedIn. I am with Command Prompt Inc. I'm also with the PG Central Foundation, which is the nonprofit behind that lovely People Postgres data sticker that you guys have been handed. We run PostgresConf, which is the largest Postgres conference in the world, as far as we know. We're going to be about 800 people this year. And then I am with, obviously, I'm a contributor to PostgreSQL.org, and then we have PostgresConf there. This is a professional training. I'm going to go ahead and get this uploaded for everyone to be able to download, but I ask that it not be distributed. It's not open source. This is one of the things that I do for a living, so it would be nice if I could continue to do it for a living. This training does succeed based on your participation. You're going to find that if you're not asking questions, you're not going to gain that much from this training. It is a lecture-based training. We do not, there's no demos or live action or CGI or anything like that. It is all, here is the information. If you don't understand the information, please ask me. I will be happy to try and help you understand what I'm telling you. Obviously, it's going to be a little interesting as I speak exactly one language, and that's English. So I'm a little bit behind you folks who speak. Actually, some of the people I've met in the past couple days speak multiple beyond two, which is impressive. So please participate as you can. All right, here's our table of contents. Like I said, one of the things I do move when I speak. That might be a little bit hard for the cameras, and I apologize for that. But the other option was to try and use a Windows PC in Russian, and that was going to be a disaster. So we're just going to have to use Linux, which we should be using anyway. We're going to talk about what we're doing, the GUCs, what version, operating system, copies of the curriculum, so on and so forth. There is quite a bit of information in this training. We only have 3 hours. So I will move fairly quickly. Don't hesitate to raise your hand and tell me to stop, though. Okay? I mean, that is why you're here. You're here to learn. And I just got to say thank you for being a full room. I was a little nervous. All right, let's get to the beginning of this. All right, so here's the introduction. I've got to figure out a better way to handle this. Hold on a second. That'll work. Okay. This training is designed to provide you with a comprehensive top-level view of Postgres performance and maintenance. We will discuss provisioning on-prem as well as the cloud, appropriate PostgreSQL.conf changes, and maintenance items such as the autovacuum process. Please remember this is a 3 to 4 hour training on a topic that many people take years to master. Performance and maintenance is very specific to your workload, to your hardware or cloud provisioning, and to what you are doing. A lot of people do some really crazy stuff with Postgres. If you know Oleg, you know what I'm talking about. Please remember, got out of that. In short, we will cover the most important topics, but if you are hoping to understand the genetic optimizer, you're going to be out of luck. That's not what we're talking about here. This is a practical implementation. This is not a theoretical implementation of how to get this stuff done. The GUC, or Grand Unified Configuration, is the name used to identify a variable identifier within the PostgreSQL.conf. For example, shared underscore buffers is a GUC parameter or variable. still there? Okay. This training will be speaking about the latest production release. That's obviously not true. We are talking about 9.6. However, everything we talk about here will apply to 10 and 11. There might be a couple of changes with 11, but I generally do not write curriculum for the brand new version of Postgres because it needs to settle down after release and be out for 6 to 9 months before you can get solid production information from it. So this is, I would say, one version back, 9.6, but like I said, it will apply. The operating system used to write this tutorial was Ubuntu 16.04, which is an LTS release. You should never run Linux unless it's an LTS release. I don't care if it's Debian or Red Hat or CentOS or Ubuntu or whatever, but if it is not an LTS, a long-term support release, you should not run it in production. You also should probably avoid what I would call proprietary forks of Linux when you're doing on-prem. I'm not going to mention any names, but they tend to be cloud-specific versions or other database vendor versions, things like that. Let's see if this will work here. Oh, that didn't work. All right. Okay, provisioning. As with any database deployment decision, you first start with your hardware platform. Nowadays, that platform may be virtual or physical. That's actually been the case for a really long time. Anybody who's been doing this as long as I have realizes that the cloud is nothing new. People have been doing it since the 90s. It was called virtual hosting. Common virtual platforms are obviously RDS, EC2, GCE, KVM, and VMware. For those who don't know, RDS and EC2 are Amazon, GCE is Google, KVM is the Linux native, and VMware is VMware. Physical platforms are software, rack space, and of course on-premise hosting within a data center or even under the desk. The rules for provisioning within these environments are similar, but there are a few key differences. Every database needs volume performance. This is true whether you are using a DAS, a SAN, or a NAS. Let's talk about a DAS versus SAN. DAS, or direct attached storage, has a number of benefits over a SAN or a NAS. The most obvious of the benefit is cost. A DAS solution is always significantly cheaper than a comparative SAN, spindle for spindle. The other DAS benefit is simplicity. Come on. This is going to be rough. Okay. A directly attached disk will always have better price per dollar than a SAN or NAS. You also can't beat direct attached storage for simplicity. With file systems such as ZFS, it is possible to get a full range of SAN NAS features with your direct attached storage at a much less cost. However, these rules are changing due to widely available open source projects such as FreeNAS. It's also changing because as people move to the cloud, the interconnects to the cloud are much faster. When I got into this business, the fastest interconnect was 12 megabit. Now we've got things like 128 gigabit, if you've got the right hardware. The DAS cons, although it is possible to get much of the redundancy that SAN provides, you cannot get all of it. In order to expand your volumes, you will need to use a volume manager on Linux, a common occurrence, or a smart file system such as ZFS. This is particularly important on Linux because LVM is not good. There's no other way to put it. LVM is a very lazy implementation of what other people have figured out decades ago. And I one time used to teach curriculum on backup and restore and file snapshots and things like that. And when you compare things like file snapshots with LVM compared to ZFS, it's embarrassing. LVM is just not that good at it. So you do need to kind of be careful when you're trying to deploy your own do-it-yourself solution. It is also using it as a shared resource is not as reliable as a SAN. That isn't to say that Linux, IPSCSI or NFS is bad implementation. It's not. But it is to say that if you buy a SAN, you've got billion-dollar corporations who have, I don't want to say perfected, but I'll say fine-tuned their particular implementation for sharing the volume. All right, SAN pros, management. A SAN generally has an excellent management features, including dynamic allocation of space, excellent redundancy, and resource management. It can also be used easily as a shared resource. It's pretty impressive what you can do with a SAN nowadays. You can get better performance out of a SAN via multipath. New versions of Fiber Channel can reach 128 gigabits per second. I think that's actually out of date. I think we can go faster now, but I haven't checked. The cons of a SAN is cost per spindle. The cost per spindle is much higher, exceedingly higher than a DAS solution. Direct attached storage is just cheap. Even nowadays, you can get, if you look at some of the Intel enterprise SSDs and how fast they are, even comparatively, you throw those into an appropriate server chassis and you're going to be flying at a fraction of the cost of what a SAN would cost you. Let's make some sense of all this. The short of it is, when provisioning for Postgres on spinning metal, SATA, SAS, SSD, or both spinning metal, not SSD, you want a hardware-based RAID controller, battery back cache, and you want to run RAID 1 or 10. Do not run 5, do not run 6, run 1 or 10. Those are the only database RAID levels. Volumes in the cloud. What the heck just happened here? There we go. Where are we? Okay. The average SAS drive can perform at approximately 25 megabytes per second of random write performance. Every write that PostgreSQL performs sans the transaction logs is a random write. Sequential performance is not that important. Even the slowest drives you can purchase have a decent sequential write performance. However, I'm curious how out of date this is, and what I mean by that is, who here is running Postgres on spinning disks? Anybody running spinning disk versus SSD? Is it data warehouse or is it OLTP? Sure, okay. If you only have 25 megabytes available per spindle to get reasonable performance out of the database, you need RAID 10, which requires at least 4 spindles. The default RAID 10 configuration is only going to give you 50 megabytes per second. That is a stripe over 2 mirrors. The mirrors are going to give you 25 megabytes each. Now, why this is particularly important is that the SSD in my laptop is 10 times as fast as that. And that's just my laptop. So when you're provisioning, if you're thinking to yourself, should I get SSDs? The answer is yes. The only reason not to is if you are doing many, many terabytes of data warehouse type stuff where you need to have 100 spindles that are 4 terabytes a piece or something like that. If you're doing any kind of reasonably sized OLTP where you're talking 1 terabyte to say even 50 terabytes, see if you can afford the SSDs. The speed is just going to be so much faster. The use of a battery back cache can greatly increase the performance of your RAID implementation because Postgres is writing to memory and the controller is pushing that memory to the drives. A good RAID controller optimizes those writes and writes them in a manner that is most efficient for the drives. I'm going to take one quick second here and see if I can make this a little better for everybody. Hold on. Okay, so apparently QR codes are still a thing. If you take a picture of this QR code, you'll be able to download this curriculum. So we'll just take a moment while everybody, I'm just going to duck. The use of a battery back cache can greatly increase the performance of your RAID implementation because Postgres is writing memory to the controller and the controller is pushing memory to the drive. Why is this important? Because good controllers with good drivers actually know how to optimize the writes to the drive. It's not just random. It doesn't just sit there and go, hey, I hope it wrote to disk. It's actually pretty smart about it. But who runs spinning metal anymore? Use SSDs. This is an older version of the data center P3520 SSD from Intel, but it does have the following specifications, which is pretty interesting. It's 100 megabytes, not bits, bytes per second. So it's 26K IOPS, random write at 4K. That's four SAS 15K drives on random write. It's 1,450 plus megabytes per second, which is 375,000 IOPS, random read at a 4-block size. Most databases are what? They're mostly read. And of course, it's random because it's Postgres. Now, if you were to look at the specs of the newer Intel stuff, it far blows this away. It's amazing how far they've come in just the 3 years since I've done this research. The further advantage of SSDs is concurrency. They can handle many more requests than a spinning drive. The average 15K SAS drive can only perform about 150 IOPS. That's not that much. A second, 150 IOPS a second versus what you see above. 1 megabits equals IOPS times kilobytes per I/O divided by 1024. Why did you not? Okay. Volumes and the cloud. This has gotten better over the years. It used to be you had to be very, very careful. But when we are talking about the cloud, we're talking about something like an RDS or an EC2 or a GCE. Anybody here, it's kind of a silly question, but anybody here on RDS or GCE or anything like that? How many of you are still on-prem? Meaning you host your own database. Okay. RDS, EC2, here's where you can find the docs, but here's some general tips if you're dealing with volumes in the cloud. When you're dealing with we're going to talk about Amazon specifically. We could talk about GCE. GCE is actually a lot simpler. But with Amazon, you want to make sure that you pay attention to the differences because they have what's called general purpose SSD, which is GP2, versus provisioned IOPS SSD. And now they even do things a little different because they actually based your IOPS on the amount of drive, amount of space that you're allocating. And if I remember correctly, it's 3 IOPS per gig. So if you have 1 terabyte of volume, you've got 3,000 IOPS. And that really isn't that much. You'd think it is, but it's not. I mean, if you do the math of a 15K SAS drive is about 150 IOPS, and you only have a terabyte on the cloud volume, and it's got 3,000 IOPS, you can kind of figure out how many SAS drives you're talking about in performance. Specifically, what you want to pay attention to on something like Amazon is your volume sizes that are available. So with a GP2, you've got 1 gig versus 16 gig, or not gig, 1 gig to 16 terabytes versus the provisioned. I'm not going to talk about spinning with EC2. 4 gigabytes to 16 terabytes, but your IOPS are particularly interesting. So on GP2, you max out at about 10,000 IOPS. On provision, you max out at about 20. I think they can go a little higher now. I think they're at 25 or 26 now. When this was written, it was at 20,000. But where you start to see your major differences, and this is where you want to pay attention. A lot of people who run Postgres think I can save a ton of money by using your general purpose SSDs, and you can. And especially if you pay attention to the IOP allocation per size. But there are limitations in that the max throughput for your particular volumes. You have a max throughput of 160 megabytes per second with your general purpose, but you can go 320 megabytes per second with your provisioned. And your max IOPS per instance, of course, 75,000 and 75,000. Max throughput per instance, 1750 megabytes versus 1750 megabytes, and the dominant performance is IOPS. Now that we're out of the cloud. Okay, so let's talk about processor. Postgres is process-based. It's not threaded unless you use I think it's Postgres Pro has a version that's threaded. Put simply, the more cores, virtual or otherwise, you have, the higher connection count and transactions per second you can expect to be able to maintain. Of course, assuming other variables such as proper configuration, memory, and volume performances are in line. Why does this matter? CPU vendors, specifically Intel, likes to talk about how there are 4-core, 8-core, 16-core, whatever the chip is you're doing is very, very, very fast. But the reality is, and the secret they don't want you to know, is that all CPUs are fast now. They've been fast for years. And when you're dealing with something like Postgres, unless you're dealing with a very specific type of workload, a previous generation CPU with lots of cores is going to be more effective than a newer generation CPU with less cores. And that's based on the architecture of Postgres itself. Consider the following GCE configuration. For those who don't know, GCE is Google. It's their answer to EC2. If you say you've got a 500 gig SSD, which 240 megabytes sustained, random write, at 15,000 IOPS. I did test this. We actually do get it. Running Postgres 9.6 with synchronous commit off. Synchronous commit off is a huge performance benefit, and very rarely do you actually need to leave it on. There are times, especially when you're talking about like synchronous replication and things like that. But as a general workload, you don't need it. Using IO zone, here is what we see. So basically boiling it down, if we look at the random write, we can see, so children see throughput for 4 random writers. It's about the middle of the screen. We have 238 megabytes per second. So we know that we're actually getting the performance that GCE is telling us that we're going to get. Now, assuming we have this great performance, the 240 megabytes per second, we have configured our instance connected to this SSD. Here is some workloads. I used benchmark SQL for this. Don't use PGBench. PGBench is not a realistic benchmark on any stretch of the imagination. It gets CPU bound. It's a useful utility, but it is not a useful benchmarking tool. Use something like benchmark SQL, or even some of the commercial versions, which are much better at driving Postgres so you can see where your faults are in your performance. But if we take this configuration, we have 4 CPUs and 15 gigabyte of RAM. Okay? So we have 4 workers, that's connections. Okay? We're going to get 476 transactions per second. This is on a pretty standard, simple virtual machine on Google. If we have 8 workers, notice here, 8 workers versus 4 CPUs, okay? 653 transactions per second. Now, if we have 12 workers against these 4 CPUs, we hit 661. Now, I ran these benchmarks multiple times, and they were all within noise level of the same results. And why this is important is that it used to be before 9.6, and actually it was before 9.2, on 4 CPUs, our max performance would have been at probably 4 connections, 4 workers. But now with 9.6, and especially 10 and 11, the scale is different. And that is largely due to the work of Robert Haas with a lot of the locking and shared buffers work that he has done. It's some really amazing work. And you can also see that as we continue down with 16 workers and 32 workers, that our performance is starting to drop. What we're starting to see is CPU contention against the fact that we only have 4 CPUs. So there's too many processes, too many back ends trying to utilize CPU time. Okay? Now, if we step it up a notch and we go to 8 CPUs, if you look, we see 8 CPUs with 30 gig of RAM with only 8 connections, we see a huge performance boost. This is where you're starting to see the graph of how connections and processes work together to produce performance with Postgres. This is why CPU count or core count is more important than the generation of CPU that you're running. It's also why back when who remembers the Opteron processors, the AMD Opterons? Yeah. Okay, the AMD Opterons, they were beautiful. You could buy a $40,000 machine from Dell that would have 64 cores, 256 gig of RAM, and Postgres would just fly. Now, granted, if you were to compare it core to core with the Intel offering was faster, but they actually didn't have the core count, so Postgres would perform faster on AMD at the time. And I actually expect that trend to start to continue now that AMD is back in the CPU game. That being said, if we look here, once again, we're getting to the point where the cyan color here at 32 processors, so at a 4-to-1, we see our maximum TPS, 1,509 TPS. After that, we start to drop down again, and it's pretty significant at this level. The more cores you have, the more contention you have, your drop-off is going to be more immediate once you reach the threshold. So we're talking at 64 CPUs, instead of getting the 1,500 at 32, we're not even getting 1,200 at the 64. So again, this shows why it's more important to have lots of CPUs or lots of cores than less cores that are faster. Now, if we continue forward, 16 CPUs and 60 gig of RAM, you'll see that the inverse starts to become true. 8 workers only does 1,800 TPS. And the reason is the workers just can't go any faster. Our machine is over-provisioned for the work that we're actually doing. But you do start to see an immediate jump when you go to 16. And then even a bigger jump at 32. We're getting 2,800 CPU or TPS transactions per second. So again, we're starting to, and one of the things I found interesting about this benchmark, and this might be a 9.6 thing, I haven't tested it with 10. But if you look at the 4 CPUs and the 8 CPUs, it's a 3 times to 4 times multiplier at your best transactions per second. But with the 16 CPUs, it's a 2 times multiplier. We're not getting that higher level. In fact, if you go from a 1-to-1 to a 4-to-1, your TPS is similar. So what are we running into here? Why is that happening? Why isn't the trend continuing? Well, I can show you in the next benchmark right here. If you look to the left, the box, we've got 16 CPUs with 60 gig of RAM. We already know that. But I changed a few settings in the Postgres.conf. The previous PostgreSQL.conf was default. I think the only thing I changed was checkpoint timeout. Okay, but other than that, it was default. By changing a few settings, I upped the shared buffers to 32 gig. I upped the work mem to 32 gig. I dropped the random page cost to 1, which means it will favor indexes. I changed my checkpoint timeout to an hour. I increased my max wall size to 5 gig. And here's the kicker. The database is only 25 gig. Why is this important? Because the database fits in shared buffers. And since the data set, my active data set, everything that's being queried as fast as possible, is in shared buffers, which is a cache, now we're getting a huge jump. 128 connections to 16 CPUs is 2,800 transactions per second. Now keep in mind, one of the things that's happening here is we're actually I/O bound. We would have went faster if I would have had more than 240 megabytes per second. If I would have taken, say, 4 of those SSD volumes and put them in a RAID 10, we would achieve a faster TPS. But there's a couple takeaways here, and that is remembering that memory is also important to help resolve contention for the process-based architecture. All right, so last but certainly not least, the rules of memory are this. Buy more than you think you need. That's number 1. I cannot stress this enough. As a consultant, I run into this all the time where people will say, well, we only need 64 gig. Why do you only need 64 gig? Because our data set is only 32 gig. Okay, but what about your queries? What about concurrency? What about work mem? And let's be honest, memory's cheap. It's very, very cheap. I haven't seen expensive memory in decades. The last time I saw truly expensive memory was man, it must have been 99, 98. One of the Taiwanese factories got flooded, and global supply just shrunk overnight. So definitely buy more than you think you need. I know you can actually get a terabyte for quite a bit less than 2K now. I mean, quite a bit less. If you can buy more than the size of your databases, definitely do so. I mean, we showed that in the last track, right? Where if you have more memory than your data set size, you can force all of your active data set to be cached, which will increase your concurrency and your TPS exponentially. If you can't buy at least enough to get your active, if you can't buy at least enough, try to buy enough to get your active data set into memory. And I thought I covered it, but I don't. There is a way to find your active data set. If you install PG buffer cache, you can actually find out, just let your database run normal, and then you can use PG buffer cache to tell you, these are my top 10 relations. These are the ones that are always getting hit, whether it be the sessions table or the password table or the invoice table or whatever it is. These are the ones that are always getting hit. And it will tell you exactly how much memory in shared buffers that they're using. So you can actually provision, you can say, okay, we know right now we have enough, but in a year's time we're not going to have enough, but we have to live with this hardware for 3 years. So you're going to be able to at least reasonably assess, okay, let's install this much memory. If you can't buy that much, fall back to your volume speed. Make sure your storage is fast. The way you make sure your storage is fast is you run SSDs. It's just that simple. Unless you want to run hundreds and hundreds of spindles, just get some SSDs. If you review the above TPS numbers, which were up here, you will see that we get very respectable performance at 128 workers against the 16 cores. In fact, we get similar performance to the 32 worker run. This is because the size of the database is 25 gig, which completely fits within shared memory and the file cache. With all these pictures, I'm going to start dancing. Okay, the PostgreSQL.Conf is the main configuration file for PostgreSQL. We know this. We are not going to cover every setting in the PostgreSQL.Conf. There's an entirely separate training for that. It's called PostgreSQL.Conf A to Z, and it is literally 8 hours of me explaining every single parameter in excruciating detail. And I'm tired because I'm from Washington State, which is on the other side of the world. So here's the basic syntax. The file consists of lines of the form name equals value. The equal is optional. Don't make it optional. Just don't. The equal's there for readability. Leave it there. I have a saying, and the saying is don't be that DBA. I know a lot of really brilliant people, far more brilliant than myself. And what I've found is that a lot of really brilliant people like to make life very difficult for those who are not as brilliant. Don't get rid of the equal sign. The readability is important. The parsability, not only from a mental standpoint, but if you want to script anything within it, is important. You can use it as a delimiter, things like that. And yes, I know you can use space as a delimiter. Comments. The file uses standard Linux Unix style commenting style of just hash. This is a comment. Here's shared buffers. This is also a comment. And then commenting out shared buffers. Values that are comment out on the initialization of the cluster, which is initdb, are the default values as configured by PostgreSQL on install. If you wish to reset a value, you must at a minimum reload the server. There are values that require a restart. Who's been using Postgres since, trying to remember when it changed? Let's say 7.2. Anybody been using it that long? So I've been using it since before it actually existed, which is Postgres 95, PostgreSQL 95. It used to be, and we actually in the community had an argument about this. It used to be that if you were to say set shared buffers to 4096, and let's say the default was 2048, just for sake of argument. and you set it to 4096, you reboot, because you have to reboot, or not reboot, but restart Postgres in order for the 4096 to take effect with shared buffers. You're running 4096 as shared buffers. But then you decide that's too much, and you want to go back to the default of 2048. Now, most people would think, okay, I'm just going to comment it out and then restart again, and it'll go back to the default. Right? That's the logical thing. That's what every single Linux program on the planet, Apache, all of it used to do. Postgres, I kid you not, we had to argue whether or not commenting out a value should reset it to the default. We had to have that argument. It obviously now does reset to the default. If you've been doing this as long as I have, if you've been in open source as long as I have, you know that open source people like to argue about the most ridiculous things. But there it is. All right, displaying values. The recommended way to show a value as presented to PostgreSQL is via the show command, show shared buffers. Shared buffers, 128 megabyte. You can actually also get this from a system table called PG_settings. If you want to get all your, if you don't want to, for example, if you don't have shell access and you don't want to run through an iteration of every command that you know, show shared buffers, show workmem, so on and so forth, you can query PG_settings and get a specific setting. It's also very useful for automated monitoring and auditing, so that you can have monitoring that says, I know that my shared buffer, or even better, my workmem is 4 megabyte or 16 megabyte, and then your monitoring can alert you if that ever changes. Because who here has been in a position where someone, I don't know how to put it, someone who's a subordinate changed a setting, didn't document that change, and things went weird on your database and you don't know why? Well, yeah. Is that right? Exactly. And my favorite actually has nothing to do with this. My favorite is when you still have that boss that thinks he's still good at databases, and he forgets things like the where clause in a delete statement, and the fact that you never, ever, ever, I don't care who you are, how good you are, I don't care if you're Tom Lane, I don't care if you're Oleg, you do not run delete outside of a transaction. You never do that. And if you do, I hope you have point-in-time recovery running. All right, so overriding values. There are multiple ways to override values within PostgreSQL. You can edit the PostgreSQL.conf directly. Don't do that. I know it's old school, and frankly, I'm guilty of this. Even when, for those of you who might attend my replication training later in the day, thank you if you do. You know, when I was writing that curriculum, I edited the PostgreSQL.conf directly. It's because I've been doing this for so long, it's almost muscle memory. Don't do that. Use alter system. Alter system is the appropriate way to change your PostgreSQL.conf file, period. You can also use set. Set's different. It's usually session specific. So let's talk about editing the PostgreSQL.conf file. We all know how to do this, although, are there any Joe users in here? Okay. VI? I'm sorry? Emacs? Emacs? What do you guys use? Usually when I stand in front of people, I'm like, who's using VI or Emacs? It's like 98% of the room. What's the Russian editor of choice? VI, yeah, okay. You just didn't want to say it. Okay, you should be embarrassed. No, okay, so now I do know how to use VI. In fact, the reason I know how to use VI is because I know how to use ed. I've been doing this that long. But I use Joe, which stands for Joe's own editor. It is, and where this came from is I used to work at a bookstore back when I was a young man. And this gray-white monstrosity didn't exist, nor did this. And I had not been introduced to Unix or Linux yet. And I had a buddy, his name was David Ulrey, who said, I think at the time he said use Nano, and I hated it. And he said, try Joe. And I said, okay, so I tried Joe, and Joe basically is a text editor that works like the old word processor. I've used it for so long that there's actually a rule in my company, even though I very rarely log into client machines nowadays. The rule is, if we're provisioning for a client, one of the first commands you type is whatever install Joe. Because if I get called at 4 in the morning because someone didn't pick up their phone who was actually on call, and I have to fix the problem before I fire them, Joe better be installed. All right, so Joe, PostgreSQL.conf, as you can see here, we have workman commented out. We then uncomment it so it takes active. Obviously, there's no difference here. They both say 16 megs. But that is how you would uncomment it. And then if you're running a reasonably modern version of Linux and you are not one of those people that, for whatever reason, will not use systemd. I'm not saying systemd is the solution to all problems. In fact, I don't even care, but it is where the Linux world went. You would do sudo systemctl PostgreSQL reload. You can also use PGConf reload. All right, set. Set's a little funky. The use of set is reserved for session, local, which is a transaction, and testing. It will only take effect for cases that you invoke it. The use of set without an optional keyword assumes set session. If you choose to use set session within a transaction, this is why it's tricky. The following rules apply. If the transaction is aborted, the value will be reset to the system configured value. So if you are in a transaction and you say, for this transaction, I need 64 meg of work mem versus my default of 8 meg of work mem. And then you run a transaction and it aborts. You roll it back or whatever. It will automatically default back to whatever the system has set for work mem. If the transaction is committed, the value will continue to be used until the end of the session or until the value is reset via set or reset. This is important. So what's happened is you have a very specific query that you know because you have profiled it, you've analyzed it, you've explained it, you've yelled at it, and you know that when you run this query, you have to run it in a transaction, just in case, and you need more work mem, but you only want the work mem available for that query. The problem is that when you commit whatever that query is, as long as your connection is active, it will stay at whatever you set it to. So if you set it to 64 meg, and you've committed the transaction, you're happy, your application is happy, your boss is happy, but then you run a particularly nasty query that has, say, 100 sorts, all of a sudden, that query can also access that 64 megabyte because you didn't reset it. Now you would say, so what? It's only 64 megabyte. Well, work mem especially is not just 64 megabyte. It is 64 megabyte per sort per connection. So if it is a query that gets run over multiple connections and has 100 sorts, do the math. It's not a pretty sight. Here's a perfect example, or just a simple example. Set session work mem equal 1 gig, explain analyze. You can do it to check how a query is going to respond to the better work mem, because the more work mem you have, it might change the plan. Set local. Set local is reserved for use within a transaction. Queries happening outside of the transaction will not be affected by the change. So, and you can actually see this take effect here. So if we show our maintenance work mem is 64 meg, and we start a transaction, begin, set local maintenance work mem to equal 1 gig, set, it's telling you, yep, we set it. Show maintenance work mem, it's 1 gig. We're still in the transaction. Reindex table foo, reindex, we now commit, and we show maintenance work mem again, and it has defaulted back. So the takeaway here is if you are changing work mem or any setting within a transaction, use set local, not set. And we talk about this again. Here's an illustration of why not set within a transaction. So we show work mem. Our work mem is 4 meg. We start a transaction. We set the local work mem to 16 meg. It sets it. Show work mem 16 meg. Okay, everything's good. Set work mem to 8 meg. Set. Show work mem 8 meg. We're still good. We commit. And then show work mem is still 8 meg. Even though we started with the default of 4 meg. Okay? All right, alter system. The main PostgreSQL configuration file is PostgreSQL.Conf. We discussed this. There is a secondary file that is stored within the cluster directory. Cluster directory is usually data, but on Ubuntu, and I think Debian as well, it's actually main. It is named PostgreSQL.auto.conf. Do not edit this file by hand, ever. Don't edit it by hand. This file is used with the alter system command and enables the permanently setting of PostgreSQL.conf values on the command line. And when I say command line, I'm talking about PSQL. I'm not talking about bash or ZSH or anything like that. The PostgreSQL.auto.conf file is loaded after the PostgreSQL.conf and will overwrite the values set within the PostgreSQL.conf. So you got two things here. Don't edit PostgreSQL.conf by hand, ever. Use alter system, because alter system will always override your PostgreSQL.conf manual changes. Here's an example. So we show work mem, 4 meg, alter system set work mem to 16 meg, alter system, show work mem, it's still 4 meg. Okay? It's because we haven't reloaded the file. We cat the PostgreSQL.auto.conf, we can see that work mem is actually 16 meg. We just haven't reloaded. We go in PSQL-UJD Postgres-H localhost, blah, blah, blah. Select PG reload conf. And what that does is actually hop the server, the postmaster process, and then we can see by showing work mem that is taken into account. I do not recommend that anybody be at the system shell for Postgres unless absolutely necessary. It is entirely too easy, even for the best of us, to make a mistake and blow away your installation in some way. If you can change it from a connection to Postgres, that is where it should be done, via alter system in PSQL, PG reload conf, or PGConf reload, so on and so forth. PG reload conf, the administrative function PG reload conf must be executed by a super user. One should always validate changes made with alter system by using PG reload conf. That's the other benefit to PG alter system. Alter system is constrained by what a valid value for the parameter would be. We can go in by hand and say, I want shared buffers to equal ABC, and reload it, and Postgres isn't going to, or restart it actually because it's shared buffers, and then Postgres isn't going to start because it has an invalid value for shared buffers. But with alter system, it's essentially typed. It would tell you before it wrote it to disk, it is invalid. It is an invalid value of shared buffers of ABC. Just like you can't put text into an integer column. It's extremely valuable. Restart, reload, and session. In this curriculum, you will see notes at the end of each parameter that will state how the parameter can be changed. If it is labeled restart, you must restart PostgreSQL for the change to take effect. If it is labeled, if it's labeled reload, you can use PG reload conf for the change to take effect. If it is labeled session, the parameter can be changed via session or made permanent via reload. For example, set work mem. Right, so if you set work mem on the session, it's only valid for that session, but you could also use alter system to change it and then reload the value. Units. The PostgreSQL.conf and associated commands to edit the file also allow for the use of 2 units for describing the value. The units are specific to memory and time. Memory units are in megabytes, gigabytes, and terabytes. I don't know if we support petabyte yet. We might in 11. The following is an example of configuring a setting for a value of gigabyte. Set maintenance workmem 1 gigabyte. This is one of those moments where don't be that DBA. If you look, there are people that do this. Set maintenance workmem to 107337411824. Now, that's obviously valid. Why are you making me math? I don't want to math. I want to know exactly what the setting is set to, and I want to move on. I'm busy. That's why we put the metrics or the units in there. Who's that? So you use the units. It makes your life easier because, I mean, some people really like math, and I enjoy math when it includes dollar signs. I mean, I really do. Even better if it's euro signs because it's better than the dollar. But I don't want to have to think, okay, is this a gig or a gig and a half or 1.2 gig? I just want to know it's a gig. So just use the units. Time units. Time units are used to easily transform values such as seconds into minutes. Currently, the following time units are supported: seconds, minutes, hours, days. The following is an example of configuring a setting for value of 1 hour. It's pretty obvious. Autovacuum nap time is 1 minute. Alter system. Notice I'm not editing the PostgreSQL.conf. Set autovacuum nap time to 1 hour. Do not ever do that. In this particular, this is an example for demonstration purposes only. Never, ever, ever set your auto vacuum nap time to 1 hour. You will eventually regret it, and it will be at the worst possible time, like at your wedding. Just don't do it. All right, now we're getting into the meat. One moment, please. Max connections. The maximum number of connections allowed to PostgreSQL, the default is 100. Remember the grid in the beginning of this discussion. 100 connections versus how many cores. You need to be careful what you're doing. The maximum number of connections, the default is 100. The cost of launching new connections is expensive. That's why threaded Postgres should have happened 10 years ago, because processes are expensive to launch. Now, it's not horrible in Linux, at least if you just observe it from a 1,000-foot view. But if you ever test a situation of, wow, that's some great water. If you ever test a situation where you are creating and dropping connections over and over and over and over, you will see your CPU utilization just crank all the way up. It'll go through the roof. If you put in a connection puller, you won't see that. Now, in threads, it's a little bit different. You don't get quite, it's not quite as expensive with threads, but we don't have that in the main vanilla Postgres. The higher number of the connections can adversely affect your performance. Each connection requires its own memory and CPU time. Connections also directly interact with the other settings such as workmem. Your max connection should be set as low as possible. I showed that earlier. If you think you need 1,000 connections, your architecture is likely broken. You are not thinking about the problem correctly. You're very well. I mean, it is. And I get these calls. You'll see them on like IRC. You'll see them on Stack Overflow. You see them all the time. I need 1,000 connections. And the response is, do not know what you're doing. Period. If you need 1,000 connections, you don't know what you're doing. I have seen some of the biggest, baddest transactional loads run on 64 connections because they were properly architected, properly cached, properly pooled, and you didn't have to worry about all that. There is a good article on this GitHub here. It's actually more about Oracle, and I know that's like evil, but Oracle and Postgres share a lot of... I'm sorry, did I offend someone by saying Oracle is evil? I'm going to say it again. Oracle is evil. Oracle is evil. Okay? But it is actually a really good article on trying to figure out your appropriate pool size and what your connections should be. And I do recommend reading it. If you modify max connections, it does require a restart. Super user reserved connections. I remember when this went in. This was another argument. Why do we need super user reserved connections? Well, I'll tell you why. Because if you don't have super user reserved connections and you run out of connections, how do you connect? It's really quite simple. You are literally out of connections. So, and yes, this was an argument, but if we finally got around to it, and now we have up to 3 connections, no matter what, are reserved for super users, which is great. Because if you have 100 connections, which you should never have 100 connections, it should be pooled, but if you have 100 connections, you know that only 97 are actually available because 3 are reserved for the boss. And the boss always needs to be able to connect to his database. My recommendation is 5, just because I've more than once found a situation where there's more than one boss, or there's the boss that runs tmux and connects from one location and then another location and then another location, and then you run out of connections. Who here uses tmux? What about screen? Okay, if you're using screen, you're doing it wrong. Switch to tmux. Don't get me wrong, I like screen. It's one of those old school tools, but tmux is comparatively, it's like running 386 BSD versus free BSD, right? They're both BSDs, but one of them is really ancient and you don't know why you're still doing it. Okay, just run tmux. If you change your super user reserved connections, you do need to restart. Now let's talk about resource usage. Shared buffers. This is the bane of many people's existence, especially if you're running an older version of Postgres. Anybody here have a production version of Postgres that is below 9.2? There's got to be one of you. There's always one. Nobody? I once asked this question, and I felt bad for the guy. He kind of slumped down in his chair and he raised his hand. I'm like, so what version you running? 8.0. Now, I'm like, 8.0? You realize, and we're talking about 9.6 here, right? And he's like, yeah, I just haven't gotten around to it. I'm like, okay, well, how big's your database? Because I figured, okay, maybe it's a hobby database. Maybe it has like 256 meg in it, right? No big deal. So what? It's 8.0. It's not like it didn't work back when it came out. The guy had 2 terabytes sitting in 8.0. Don't do that. It's like buying a Yugo now, right? Who remembers the Yugo? Come on. Someone remembers the Yugo. You do? Yes, the Yugo. Yugo was the former glorious, I don't know if it was a republic, but the former glorious Republic of Yugoslavia's car. They actually shipped this thing to the States. It lasted about 3 weeks. Just don't do it. Anyway, so shared buffer pool is the cache that maintains the status of hot data, meaning data that is in active use. This, remember when I was talking earlier about using PG buffer cache to see what your active data set is? This is what we're talking about. And actually, I'm going to show you an example here. In older versions, previous to 9.3, the common wisdom was to set this to approximately 25% of your available memory for PostgreSQL. So if you had, let's say, 4 gig, you would set shared buffers to 1 gig. Nowadays, that is no longer the case. 9.6 and up, you can crank this setting way up, and it's very advantageous to do so. And actually, even in 9.3, you could set it higher. But as I'm sure you're aware, every release of Postgres, we just get that much better, and we make everybody look that much worse. So we're getting much better at this. When we're in production, we can use the extension PG buffer cache to assist in managing this setting. So here's an example. First, to change shared buffers, you do need to restart. But here's a query that will tell you exactly what your top 10 active data set rows are. Because let's be honest, a lot of us don't have 2 terabytes of memory. Okay? A lot of us are stuck in the 32, 64, 128 gig land. And we have data sets that are larger than that. So this allows us to say, yeah, I've got 64 gig of RAM, and yeah, I have 500 gig or even a terabyte of data. But so what? What we care about is the data that is always accessed. That data is the data you want to make sure is cached. Because no matter what, unless you're using the absolute latest, I don't even remember what they call it now, but there's this new Intel hybrid RAM/SSD thing that's almost as fast as RAM. Unless you're doing that, hitting the disk is expensive, even with an SSD. So what this allows you to do is say, hey, give me my top 10, and as you see, I've got them here, and then you can add how much shared buffers I actually need. Now, I don't recommend making this exact because it changes, and you want some buffer for the buffers. But taking the amount within an appropriate level, if you have the memory available, and say adding 25% to that, so I don't remember what this equals out to. I don't know if I say, I don't. But let's say, just for sake of argument, this equals out to 24 gig. You would say, okay, I'm going to set my shared buffers to 36 gig. It gives you room to breathe. And also, if you go under load, where you're under high concurrency, because shared buffers keeps a copy of every version of the tuple that is active until committed or evicted, it gives you some room to make sure that there's extra room for the data to be processed within buffers. So here's the explanation. It's the top 10 tables in the cache and how many buffers and the shared buffers memory total used. Remember when tuning that you have to account for every database. That's an important part. If you have a cluster with 10 databases, you have to run PG buffer cache in every single database and then do your calculations and then make your setting, because databases are isolated from each other. There is a correlation to the background writer, which we will discuss later, and PGStatBG writer. The default share buffers is 128 megabytes. It is too small, period, the end. One of the really great things about PostgreSQL is that we still develop like we're going to be deployed on very old hardware. One of the worst things about PostgreSQL is we still develop like we're going to be deployed on really old hardware. It's one of these catch-22 things. You know, in a lot of the world, it is unheard of to have, say, an i7 Xeon. Right? They're running something 6, maybe even 8 generations back, and they're happy about it. So it's really great for us to be able to say, yeah, you can still use Postgres, because I dare anyone to deploy Oracle Evil Advanced Server on like an i5 from 5 generations ago. You know, it's just not a good idea. But we can actually still give pretty decent performance at that level. Okay. Huge pages. This setting is only available. Who is running Postgres on not Linux? What do you got? Windows. Is it a lot of Windows folks? Yeah, okay, that's pretty common. Oddly enough, so if I ask this in the States, even if there are people that are running on Windows, they refuse to admit it. Which is actually a shame, because Microsoft is doing some really great things with Postgres right now, lately. But yeah, so huge pages, which is only available on Linux, enables and disables the use of huge memory pages. This can be a huge benefit. We're not going to get deep into it because it's a deep discussion. I could probably do an entire presentation on what huge pages are. And we're not talking about transparent huge pages. We're talking about huge pages. They're different. And how to set them to see the benefits. If you're interested, go ahead and Google huge pages Citus. I think it was Citus that did it. They have a really good blog that shows the recent performance gains with huge pages. And there's also a great intro to it from Debian on how to set it. But the short of it is, Without huge pages, when a process uses 1 gigabyte of memory, that's 262,144 entries, 256K essentially, 256K entries to look up and manage 1 gig of memory, of data. On my 4th generation i5 workstation, I have the ability to use 1 gig pages instead of 4K pages. Instead of using 256K pages to manage 1 gig of memory, I'd be using 1 page. Now, for most of us, we never, ever, ever notice this. But if you're under a very heavy, high concurrent load, you can see your overall CPU load greatly drop just by changing this one setting. And people don't think about it. They're like, huge pages try, okay. But if you change, whatever. But if you actually set it and you test it, there's a very good possibility it will help you. It is a restart to change that. Okay, temp buffers. This is a misnamed parameter, and if any of you have done any explain, how many here, I mean, obviously probably all of you, you've all had to run explain, right? Okay. Explain has some weird terminology in it that actually does not directly correlate to anything. They just assume you know this, which is unfortunate. But this is a misnamed parameter as it only applies to temp tables. Okay, so it's temp buffers that only apply to temp tables, e.g. if you say create temp table. This is the total number of temp buffers that can be used for a temp table represented as local in an explain plan. Get where I'm going with this? Why it doesn't make any sense? We have temp buffers that equal temp tables that equal local in an explain plan. Before the temp table will swap or spill to disk in a tape sort. If you are an active user of temp tables, consider increasing this value as it will keep temp tables in memory instead of spilling to disk. It's a very common problem. If you use temp tables, you think they're going to be super duper fast, but you're using them for a lot of data, and then you find out they weren't as beneficial as you thought because everything's spilling to disk. Well, you can increase temp buffers so that it doesn't spill to disk. It does require a restart. Workmem. This is possibly the most theoretically dangerous setting in PostgreSQL.conf outside of the most real dangerous setting, which is fsync. This is the working memory available for operations. It is calculated per connection per sort. Go back to the person that thinks they need 1,000 connections. That 1,000 connections is running queries with an average of 4 joins. Each one of those is a sort and a where clause and order by. Do the math. It gets ugly really quick. Historical recommendations are to treat this parameter conservatively. However, if you have a reasonable amount of memory, it is possible to set this higher to encourage use of memory sorts over disk. This is true. Even myself, I have worked on literally thousands of installations for Postgres. And for years, I was like, if you want to change it at the session. Right? If you had a query that you knew needed more workmem, just use set workmem blah, run your query, and just move on. Don't change it in the configuration file. The problem with that idea is I'm not a developer. I'm a DBA. So I actually do things right. Developers like to connect to the database and think they know better than the database. And so they would do weird stuff with workmem, and you'd wonder why all your resources were gone. And their response is I'm responsible for this module in an application with this many modules, and my module is more important than yours, and therefore I must use more memory. It's better just to try and find a reasonable setting within PostgreSQL.conf. If you've got a reasonable amount of memory, it's not a big deal to set it to, say, 16 or 32 meg or even 64 meg. Just pay attention to what you're doing and make sure you got proper monitoring. Here's an example of knowing how much workmem is being used from explain. Here's my sort method, external merge. I have merged to disk for about 19 meg. Buffers, I hit about 25 meg, I read that many, and I wrote that many. The first sort is a disk sort. In short, we swap to disk to process the merge. Terribly inefficient unless you're running lots of SSDs. The whole query read 800 or 8,822 temp blocks. Okay? Remember what I was saying about explain, not really explaining anything? And wrote 8,808 temp blocks. The above are all caused by overflowing work mem. We've overflowed work mem, so all of that is getting swapped out. The temp read-write is in blocks, and blocks are what? 8K. Postgres blocks are 8K, just like its page file and its page size and all that. So if we do the math, approximately 19,352 megabytes plus my temp blocks times, I lost my train of thought, I apologize. So 8808 written temp blocks equals 8192 because it's each block. So 8K times 8808 equals 72 megabytes. So to not overflow work mem, we actually need a work mem of about 100 megabytes because it's the first, the 19-ish megabytes plus the 72 megabytes. So that's why it's a pretty dangerous setting. Now the great news is you don't need to set it to 100 megabytes, right? You could double your performance just by stopping the disk merge. Just that first 20-ish megs, right? So set it to 32 meg. You don't get the disk merge, but you're still writing the blocks. Trying really hard not to be too American here. It is something you can set at the session as well, which we discussed. Maintenance work mem. I think we're getting close. When's the break? Anybody? Just about now? All right, I'm going to finish maintenance work mem, and then I'm going to sit down for a minute. Similar to work mem, but used for maintenance tasks such as vacuum, autovacuum, and reindex. It is allowable amount of RAM to be used before the process will switch to disk to clean up. It is session modifiable. This is not something to be scared of unless you are very resource constrained. If you've got 32 gig of RAM, set it to 2 gig. I think they removed the limitation now, but I think in 9.6 your max I think is 4 gig. You can set it higher, but it will only use, I think it's 4 gig. But go ahead and set that up because you don't want vacuum to be slow, ever. You don't want reindexes to be slow, ever. And reindex concurrently is not always an option. All right, let's take a break. Okay, before we get started, as we start a marathon to get through this, Amanda, who is my operations and project manager, wanted me to let people know that if you didn't get stickers, they're right there on the corner. We have a People Postgres Data sticker, which is really cool. It's the mission of PostgresConf. And then we have the command prompt Mammoth, which has some story behind it. Command Prompt was actually the first company to create an integrated replication system for Postgres. It's no longer in development because obviously Postgres has replication. But all that stuff that it took them until version 10 to get, we had all the way back in 8.3. But he's a really cool little elephant or a little mammoth. So please feel free. And then if you want, my business cards are there as well. I know most people use like LinkedIn and stuff, but you're more than welcome to my cards. I might as well get rid of them. I've got thousands. Okay, let's get started. We got a ways to go. So now let's talk about kernel resource usage. This is likely not going to have too much to do, or at least the first one won't have anything to do with your Windows folks. I have no idea how to set this on Windows. But it sets the maximum number of files that can be simultaneously opened by each server subprocess. The default is 1,000 files. Very busy servers will overrun this. It's pretty easy to change. You just say, if the kernel is enforcing a safe per process limit, you do not need to worry about this setting. If you find yourself seeing too many open file failures in your logs, try reducing this setting or increasing the Linux kernel max file setting, which is in procsys fs file max. And it's live. You don't need to reboot or anything like that. You just change it. Things will be good. Shared preload libraries. This is actually a really nice feature. I don't remember when it was added, but it's been a while. It specifies one or more shared libraries to be preloaded at server start. This parameter can be only set at server start. If a specified library is not found, the server will fail to start. But it will also log, can't find this library. Some libraries need to perform certain operations that can only take place at postmaster start, such as allocating shared memory, reserving lightweight locks, or starting background workers. Those libraries must be loaded at server start through this parameter. This parameter can also help with performance of certain libraries as they are loaded on Postgres start versus called externally. Specifically, I think one of the ones that's common is PGStat statements. You can't use that without shared preload libraries. It's a really hefty process, and so you want to preload it so it's in RAM and it won't affect the performance nearly as much. I haven't tested this recently, but there has also been some rumors that if you use some of the external procedural languages like Python or Perl, you can preload their shared library so it doesn't have to call out to disk on every execution, which can be a performance benefit as well. Background writer. A lot of people don't mess with the background writer that much anymore. We've gotten pretty efficient with other parts of the system. I find that paying attention to it, though, is still pretty useful. This is a separate server process called the background writer, whose function is to issue writes of dirty, new or modified shared buffers. When I say writes, I'm talking about to disk. It writes shared buffers so server processes handling user queries seldom or never need to wait for a write to occur. However, the background writer does cause a net overall increase in I/O load because while a repeatedly dirtied page might otherwise be written only once per checkpoint interval, the background writer might write it several times as it is dirtied in the same interval. Meaning that as a buffer is dirtied during a time frame, it might write it more than once. Now that's okay because you're not going to allocate 50 megs a second to the background writer. You're going to allocate 5 or 10 megs a second to the background writer. Okay? And this is going to allow you to make sure that your interactive processes that are writing and causing shared buffers to be allocated are not going to pause to wait for a write and then come back. Now, under normal circumstances, you never see it anyway, right? Because it's already moving too fast. But where you will see it is if you're actually monitoring your overall performance and you're watching the trends. Your BG writer delay, this gets a little, for lack of a better word, hinky. I'm not sure if that can be translated appropriately. Difficult. Maybe complex, specifies the delay between activity rounds for the background writer. This is similar to autovacuum nap time in that it's not necessarily going to do anything, but it is the rounds, it is how much it will wait to check if it does anything. In each round, the writer issues writes for some number of dirty buffers, controllable by the following parameters. It then sleeps for BG writer delay, milliseconds, and repeats. When there are no dirty buffers in the buffer pool, though, it goes into a longer sleep regardless of BG writer delay. The default value is 200 milliseconds. Note that on many systems, the effective resolution of sleep delays is 10 milliseconds. So setting the value, setting BG writer delay to a value that is not a multiple of 10 might have the same results as setting it to the next higher multiple of 10. So if you set it to like 203, it's probably going to be 210 no matter what. BG writer LRU max pages. In each round, no more than this many buffers will be written by the background writer. Setting this to 0 disables background writing. Note that checkpoints, which are managed by a separate dedicated auxiliary process, are unaffected. The default value is 100 buffers. Remember that buffers are 8K. Okay, so what we're saying here is the max number of pages the background writer will write, the max number of dirty pages will be 8K times 100. Okay, and that's kind of how you can figure out how much bandwidth or I/O this process is going to take up, because you can say, I know that every 200 milliseconds-ish, I'm going to fire to potentially write up to 100 buffers, and each buffer is 8K. So you can figure out, okay, if there's 200 milliseconds, that means there's 5 rounds per second, give or take, times 100 buffers at 8K. You can kind of determine how much I/O per second it's going to take, or potentially take. The BG writer LRU multiplier, the number of dirty buffers written in each round is based on the number of new buffers that have been needed by the server process during recent rounds. The average recent need is multiplied by BG writer LRU multiplier to arrive at an estimate of the number of buffers that will be needed during the next round. I know this is getting a little deep. Dirty buffers are written until there are that many clean, reusable buffers available. However, no more than BG writer LRU max pages buffers will be written per round. Thus, a setting of 1 represents a just-in-time policy of writing exactly the number of buffers predicted to be needed. Larger values provide some cushion against spikes in demand, while smaller values intentionally leave writes to be done by the server processes. The default is 2. Don't let your writes be done by server processes. When you let your writes be done by the server processes, that's basically your connections. You are, no matter what, you're going to decrease your overall performance, because what happens is the server process must write that buffer to satisfy the D in ACID before it can move on to continue to process other queries and buffers. That's the whole point of the BG writer. The whole point of the BG writer is all those dirty buffers that are being created by your interactive processes, those are being written in the background instead of having the direct process trying to write and basically stuttering as it writes. Okay? So in a very simple world, you don't actually have to touch this all that often, but if you find yourself having a lot of shared buffers or dirty buffers, you're going to want to increase these values so that you're more aggressive in writing those out to the pages instead of waiting for your server processes to do so. BG writer flush after. Whenever more than BG writer flush after bytes have been written by the BG writer, attempt to force the OS to issue these writes to underlying storage, essentially fsync. Okay? Because otherwise, those buffers will come back as potentially written to disk, but they're actually still in some cache somewhere. This will say, don't let any more than 5 meg not be flushed to disk. Now, we know this works on Linux. I don't know about the other operating systems. Doing so will limit the amount of dirty data in the kernel pages cache, reducing the likelihood of stalls when an fsync is issued at the end of a checkpoint, or when the OS writes data back in larger batches in the background. This is really important because, for example, Ubuntu, I haven't checked recently, but it used to be that by default, Ubuntu was configured that it would allow up to 20% dirty buffers of your RAM. So if you have 16 gig, it would allow for up to 4 gig before it would actually flush to disk. Now that sounds awesome if you're on a desktop. If you're dealing with data, money, that's terrible. That's a horrible, terrifying idea. So this is actually similar. It's almost a response to that. What this will do is say, most people don't hyper-tune their Linux. They don't think about it. But they hyper-tune their database, so the database will try and force those flushes. Okay? Larger batches in the background. Often that will result in greatly reduced transaction latency. That's absolutely true. But there are also some cases, especially with workloads that are bigger than shared buffers, but smaller than the OS page cache, where performance might degrade. This setting may have no effect on some platforms. The valid range is between 0, which disables forced write back, and 2 megabyte. The default is 512K on Linux, 0, on Linux, 0 elsewhere. If block size is not set to 8K, the default and maximum values scale proportionally to it. Anybody here running a block size that is different than 8K? Because you'd have to actually recompile Postgres to make that happen. Okay. Smaller values of BG writer, and to change it is a restart. Smaller values of BG writer LRU max pages and BG writer LRU multiplier reduce the extra I/O load caused by the background writer, but make it more likely that a server process will have to issue writes for themselves, delaying interactive queries. Remember, this is all about performance and maintenance. This is a performance thing. If you have a process, a connection, that's what we're talking about. A user is executing queries on a connection. That is the server process. If it has to wait to do things because it's writing these blocks out, your transactions per second are going to take a nosedive. All right, PGStat BG writer. You can monitor how the BG writer is performing with its configuration with the PGStat BG writer system view. If we take a look at this, we have checkpoints time, checkpoints requested, checkpoint write time, checkpoint sync time, buffers at checkpoint, buffers clean, max written clean, buffers backend fsync, buffers allocated, and last time the stats were reset. In practice, and there are exceptions, but in practice, the most important of these values to monitor is checkpoint requested. Hands down. This value represents the number of times a checkpoint has been issued either by issuing the checkpoint statement or by overrunning your max wall size. This can be a significant performance degradation, especially if you're requesting a checkpoint continuously to high transaction or bulk load. The most common mistake in Postgres performance that people make is they do not change their checkpoint timeout and they do not change their max wall size. You will see if you are under heavy write load, you can leave everything else alone. Don't touch anything. Change those two settings. Run a benchmark before and run a benchmark after, and your TPS will go like this. And then, as you saw earlier in the original first couple of pages, if you then can get your data set to sit in shared buffers, you're good to go. Okay. Asynchronous behavior. Effective I/O concurrency. Sets the number of concurrent disk I/O operations that Postgres expects can be executed simultaneously. Remember when we were talking about SSDs and concurrency? This is what we're talking about. Raising this value will increase the number of I/O operations that any individual Postgres session attempts to initiate in parallel. The allowed range is 1 to 1,000 or 0 to disable. Currently, this setting only affects bitmap heap scans. I do not know if that's still true. It may have changed. We're a couple of releases back. For magnetic drives, a good starting point to this setting is the number of separate drives comprising a RAID 0 stripe or RAID 1 mirror being used for the database. So what they're basically saying is that if you have 4 drives, 4 spinning disks, set it to 4. Okay, because really a single drive can really only kind of do, unless you've got ordered writes from a RAID controller, 1 write per spin, right? So you don't really have concurrency. The concurrency is created by the stripe in the RAID controller. For RAID 5, we're not going to talk about that because no one in their right mind runs a database on RAID 5. Anybody here running RAID 5? Thank you. Please don't do that. Really? Don't do that. RAID 5 is terrible for databases. Great for file systems, terrible for databases. However, if the database is often busy with multiple queries issued in concurrent sessions, lower values may be sufficient to keep the disk array busy. A value higher than needed to keep the disks busy will only result in extra CPU overhead. SSDs and other memory-based storage can often process many concurrent requests, so the best value might be in the hundreds. And that is true. I've done some testing, and we'll actually get down to this graph here in a second. Actually, let me finish this, then we'll get there. Asynchronous I/O depends on effective POSIX fadvise function, which some operating systems lack. If the function is not present, then setting this parameter to anything but 0 will result in an error. On some operating systems, Solaris, the function is present but does not actually do anything. Anybody here running Solaris? Yeah? Not Oracle, but Solaris. Okay. So, Solaris is not a bad operating system. It's a shame that evil won't let it go and just let it be truly open source, or at least GPL compatible. The default is 1 on supported systems, otherwise 0. This value can be overridden for tables in a particular table space by setting the table space parameter of the same name. Table spaces are cool. If you don't know what they are, think of directories. It basically allows you to say, these tables, these relations, are over on these disks. And these tables and these relations are over on these disks. So being able to change that works really well, because think of a partitioned data set. Let's say you got 5 years of data and it's 50 terabytes. Well, in reality, you're probably only querying the first 6 months to a year of that data. So move the 4 years of data over to some big SATA array, and move the 1 year to 6 months worth of data over to the SSD array. You can change the effective I/O concurrency on the SSD array to be more appropriate and leave the larger, older data set alone. Testing with the TPC-style benchmark shows that on local systems, setting this between 0 and 48 keeps the TPS within noise level. However, testing also shows that on cloud systems such as Google Cloud Compute, setting this to anything greater than 0 results in approximately 10% performance degradation on TPS. I have tested this more than once. I don't know if it's currently true, but back when I wrote this, I was stunned, because if you look, GCE, my TPS was significantly higher with no effective I/O concurrency, versus a local disk where it was all within really noise levels. Now, the question with the local disk, and I didn't test this on my local disk, is if I would have set it to something like 200 or 250, because it was an SSD, would I have seen the benefit? Other people have reported that if you are running SSDs locally in an array, that yes, you will see a benefit by increasing this up to like 200. But I have not observed it. And I certainly have not observed it on network-based file systems like GCE or, say, Amazon with EBS or something like that. Max worker processes sets the maximum number of background processes that the system can support. This parameter can only be set at server start. The default is 8. When running a standby server, you must set this parameter to the same or higher value than on the master server. Otherwise, queries will not be allowed in the standby server. Max worker process, the reason you need this is because it has to do with anything that is background oriented, including like your parallel workers. So if you're using parallel query, which is actually quite mature in 10 and 11, it's not real mature in 9.6. If you don't have enough max worker processes, other things won't work. You'll just run out of resources. Max parallel workers per gather sets the maximum number of workers that can be started by a single gather node. Parallel workers are taken from the pool of processes established by max worker processes, which was the previous one we just talked about. Note that the requested number of workers may not actually be available at runtime. If this occurs, the plan will run with fewer workers than expected, which may be inefficient. Setting this value to 0, which is the default, disables parallel query execution. I don't recommend 0 on 10 or 11. On 9.6, it still may make sense, because parallel query is relatively limited in 9.6, but it is not in 10 and especially not in 11. You need to be careful, though, because the problem with parallel query is that by default, Postgres basically goes and says, here's my query, here's all my joins, all my sorts, and all that. And it goes, I've got this one, I've got this one, I've got this one, I've got this one, I've got this one. Merge it all together and deliver it. Okay? It's a very deterministic a way to figure out how much performance you're going to get out of something. The problem is that with parallel query, the downside is that it might go, if you think of a hand, all fingers go out on its own, collect each of the joins independently, and then come back, merge them in all together, and deliver it to you. Now that's highly efficient and it's highly effective if you have the resources. If you don't have the resources, you can actually have less performance and reduce, or I should say increase the load of your server because you're doing too many things at once. Because we don't have the ability to say, only do it if load is less than 2, or only do it if we only have less than 20 connections, or only do it if only 50% of work mem is used. We don't have the ability to do that. So you do need to pay attention to this, especially in the newer versions. It's not bad, don't get me wrong. It's a beautiful feature, and it makes Postgres scale far beyond previous versions. But the cost is you got to pay attention to it. You got to be able to manage it. Old snapshot threshold sets the minimum time that a snapshot can be used without risk of snapshot too old error occurring when using the snapshot. This feature correlates to the transaction isolation levels of serialization and repeatable read. If you have an open snapshot, a transaction, and that transaction is using the isolation level of serializable or repeatable read, and the life of that snapshot exceeds this value, you may throw an error which will cause the transaction to roll back. Beyond the threshold, old data may be vacuumed away. This can help prevent bloat in the face of snapshots which remain in use for a long time. To prevent incorrect results due to cleanup data which would otherwise be visible to the snapshot. What they're talking about here is that they're talking about long-running transactions within a particular isolation level. And if you think about serializable, the most common thing of serializable would be, say, think of the shopping cart methodology, where you have an open transaction where someone has taken and said, I want to buy X. Well, how many of us have logged into a website and said, I want to buy X, realize they've had too much vodka, and they put the phone down? Well, that transaction is still, well, I've done it. Okay. There are times when I'll get a package from Amazon, and I don't remember why. And I actually bought I don't know if you guys will know what this is, but a hammock tent. It's basically a tent, which is a hammock. It doesn't sit on the ground. You hang it like a hammock between two trees. This is a few years back, and it was one night, and I wasn't drinking too much. Well, some would argue with that. I think I wasn't drinking too much. And 2 days later, I had a tent, and I had no idea where it came from. I had to actually log into Amazon. I'm like, either I've been hacked or I need to put the bottle away. But that's what this is about. So someone says, I want one of these, and then they leave or they shop for a long time or something like that. The problem is that you're allocating that number, right? You're saying, okay, I actually only have X minus 1 left. Well, you don't want to leave it like that unless the person eventually checks out. So old snapshot threshold says, after so much, I'm just going to roll that transaction back so that people can continue to go forward. And we won't have bloat and things like that. Hammock tents are really nice, by the way. The only time I've ever been backpacking where my back wasn't sore. Okay, back-end flush after. Whenever more than back-end flush after bytes have been written by a single back-end, attempt to force the OS to issue these writes to underlying storage. This setting does not affect writes by the background writer. This is actually just like the background writer, but for server processes. So you don't end up in a situation where a server process has written many megabytes of data and it hasn't been flushed to storage. So now we're going to say, if we reach X, we're going to flush it to storage no matter what. The goal would be to never hit this. The goal would be that your background writer is configured to make sure that you never even care about this parameter. Write ahead log. It is all about the D in ACID, durability. Wall level. Sets the wall level. Options are minimal, replica, and logical. The default is minimal. If you want to use streaming replication or point-in-time recovery, a minimum of replica is required. Just use logical. The rest of them just don't matter. And the reason I say that is, yes, if you're using logical, you are going to issue more writes. You are going to use more I/O, but you don't want to have to restart Postgres when you realize you should have just listened to me in the first place. And the reason is logical gives you logical replication. Logical gives you the ability to connect to Postgres and stream to Kafka. Logical gives you the ability to connect to Postgres, and I don't know why anyone in the world would do this, but stream to Mongo or MySQL. It's logical that gives you all of those really cool, why in the world am I doing this? But it's cool, so I'm going to features. So just leave it at logical. You also need it for logical replication. It is a restart to change. Fsync. This is very simple. The default is on. Your default is on. Do not under any circumstances turn this off. You will corrupt your database. It shouldn't even be a parameter you can change. Period. Don't touch it. I don't care if it's pretty. Don't pet it. Don't modify it. Don't remove it. Leave it alone. I guarantee you, if you turn this off, you're going to end up in an environment where you are either A, fired, B, up for 3 days, or C, fired. Don't touch it. Leave it on. Yes, it's a performance hit. Make it up somewhere else. I don't care if you're bulk loading. I don't care if you say, hey, this gives me 20% performance improvement. It won't, but if it does, something else is wrong. Don't touch it. Okay? Can I be any more clear? Good. I know why. So to explain why, what fsync does is it sets so that every time you're writing to the disk, it issues a file sync from the kernel call to make sure that that data is actually on the disk. Without this setting, you are essentially being lied to continually about whether or not your data is on disk. And let's say some guy who's drinking coffee walks into your data center and goes, oops, and the server crashes. Well, no big deal. You reboot, clean it up, whatever. If you have fsync, everything comes back up. Sure, you might lose the last committed transaction or something through the transaction log, but your data is going to be consistent. You're not going to have foreign key violations. Any query you run is going to come back correctly. If fsync is off, you have Chinese in a Russian database. Okay, it doesn't work. Okay? Synchronous commit. Specify, this is a tricky one. Specifies whether transaction commit will wait for wall records to be written to disk before the command returns a success indication to the client. Valid values are on, remote apply, remote write, local, and off. This also has to do with synchronous replication, which is why you have the weird remote apply. The default and safe setting is on. When off, there can be a delay between when a success is reported to the client and when the transaction is really guaranteed to be safe against server crash, e.g. written, actually fsynced written to disk. The maximum delay is 3 times wall writer delay. When not used with synchronous replication, this is purely a performance setting. Some people disagree with me on this. I will explain why. In general, you should see about a 10% increase in write performance without synchronous commit. Notice this table here with 16 connections, and imagine if we have 64. If it's on, I get 817 TPS. If it's off. If it's on, I get 724. That's over 10%. Now, what is the actual argument here? First off, is there anybody here not running an asynchronous app? 95% of apps are now what? Web-based, something like that. The web by its very nature is asynchronous. You hit post, hits the web server, hits the middleware, connects to the database, writes a query. You got all this stuff going on before you ever even get to the database. Now, what's more likely to happen? Nginx or Apache or Tomcat dies? Or someone decides to disconnect in the middle of their session by killing Chrome? Or that Postgres died? That's what we're talking about here. If you have synchronous commit on, what it says is I must go through every single layer till I get to that connection. I have authorized, I have sent my password, I have executed a query. That query must then hit the wall, your write-ahead log. The wall must write it to disk and then return back and say, I have successfully written these bytes to disk. Okay? The difference when it's off is it gets all the way down, you execute the query, and Postgres says, I got this. You don't have to go through all that wall crap. Now, people say, well, why would you do that? There's a risk. You're trusting Postgres with your data. Why not trust Postgres with your data? You do get some people that are relatively pedantic. It's okay. They're like, no, I must absolutely wait till it's written on disk. Well, that's fine. But I want to go faster, and I trust Postgres with my data. Otherwise, I wouldn't be running it. It's why I don't run MongoDB. I want a database I can trust. Okay? Anybody here running MongoDB? Yeah. He's like, okay, so quick moment. MongoDB is great, kind of. Not really. I'm just trying to be nice. So if you use Mongo for what Mongo was originally designed for, Mongo's actually pretty cool. You want to have some JSON data as an edge server that is basically a cache, right? You're not relying on Mongo to save your bank information or to process financial transactions or healthcare information, anything important. Use it to store metadata. It's great at that. It's really good at that, honestly. But when you use Mongo because you have a bunch of web developers that think JSON is like the stuff, it's like the chocolate ice cream when you should be having vanilla, that doesn't work. Use a real database for that, which is Postgres. I don't know of any other real databases. They tell me they're out there. I haven't seen one yet. Okay, I might be biased. Replication and synchronous commit. This is a big old paragraph, but it is relevant because we're talking about performance. If synchronous standby names is non-empty, meaning you have synchronous standbys, this parameter also controls whether or not transaction commits will wait for their wall records to be replicated to the standby server. What does this mean? I'm not going to go through this whole paragraph. I'm going to boil it down. What this basically means is don't run synchronous replication. Okay? That's what it actually boils down to. The problem with synchronous replication is it's slow. Very, very slow. And you are guaranteed at some point an outage. And this is why. Synchronous replication in Postgres is correctly designed by engineers. Incorrectly designed for people who have production servers. And this is why. Okay? What it says is, on my master, on my primary, I have these rights that have come across. I've accepted these rights, but I cannot commit these rights to disk until I go over the network to this other database server, and this other database server puts it in the wall, writes it to disk, and then goes all the way back over the network and says, yo, I got this. And then the primary says, cool, writes it to disk and lets you continue on. Now that is absolutely 100% awesome if we're in an environment where under no circumstances can we lose data, right? There's no arguing that. Like I said, correctly designed by engineers. Problem is, I was told that car analogies won't work, but as we know, engineers sometimes design things that are only correct until you use them. Okay? Here's your problem. If that secondary goes down, your master stops working. Why? Because you're synchronously replicating. Your master, your primary, is waiting for the secondary to say, I got these rights, you can continue. Synchronous replication, beautiful for keeping data safe, horrible for performance and uptime. Okay? The other part of this is I've run, like I said, I worked on thousands of machines. And the lag time, as long as you have the right network interconnect, for asynchronous replication is almost non-existent. I say almost because it does depend on your load, but I'd rather get 1,000 TPS versus 500 TPS as a general rule. And you're basically doubling your write load and adding a network stack if you're using synchronous replication. Okay? In newer versions, there are some niceties, like we have quorum commit, which means that you can be running synchronous replication, and as long as a certain number of synchronous servers respond that they have the data, it will continue forward. That's actually how Amazon Aurora works. If you've heard of Aurora, Amazon Postgres Aurora, what it does is when it writes everything out, one of the reasons it's so fast is it writes out to multiple volumes, and it uses quorum commit to determine when it's allowed to move forward. So it's a nice feature. All right, wall sync method. The operating system call that would be execute to force writes to disk. On Linux, the default is fdatasync. I've never seen anything but fdatasync be faster on Linux. On Windows, I think it's OpenSync that they recommend. Full page writes. When this parameter is on, the PostgreSQL server writes the entire content of each disk page to wall during the first modification of that page after checkpoint. Do not turn this off. It can lead to corruption. That is just the simple truth. Now, this does not apply to proprietary versions of Postgres from Microsoft or Amazon. Aurora specifically. It does apply to RDS. But Aurora and the Azure Postgres both have their own back-end storage that's different, and they do not require full page writes. Wall compression. When this parameter is on, the PostgreSQL server compresses a full page image written to wall. When full page writes is on or during a base backup. A compressed page image will be decompressed during wall replay. The default value is off. Only super users can change this setting. Turning this parameter on can reduce wall volume without increasing the risk of unrecoverable data corruption, but at the cost of some extra CPU spent on compression during wall logging and on the decompression during wall replay. Here's the thing. It only compresses full pages. Pages are 8K. Those compress very fast. CPUs are very fast. Go ahead and turn it on. Try it out. See how it works for you. You're not risking anything really because your CPUs are already fast and it can actually increase performance. Wall log hints. When this parameter is on, the PostgreSQL server writes the entire content of each disk page to wall during the first modification of that page after a checkpoint, even for non-critical modifications of so-called hint bits. If data checksums are enabled, hint bits updates are always wall logged, and this setting is ignored. You can use this setting to test how much extra wall logging would occur if your database had data checksums enabled. This parameter can only be set at server start. So by default, Postgres does not checksum its writes. Postgres has a long history of saying, we're a database, not a hardware RAID controller, not an OS file system manager. Right? So it didn't used to checksum stuff. But what we found over the years is you can't trust RAID controllers. You can't trust Linux to necessarily write things. Now, it's rare. Don't get me wrong. It is very rare. I think in 20 years, I've run into a checksum problem maybe half a dozen times in 20 years. But depending on what you're storing in your database, just once could destroy your whole company. So Check it out. Checksums are a definite performance hit, however. There is no way around it. There is no, oh, if I do this, it won't be a performance hit. No, you turn it on, it's a performance hit. Period, the end. Wall buffers. The amount of shared memory used for wall data that has not yet been written to disk. The default setting of -1 selects a size equal to 1/32, about 3%, of shared buffers, but not less than 64K, nor more than the size of one wall segment, which is typically 16 meg. This value can be set manually if the automatic choice is too large or too small, but any positive value less than 32K will be treated as 32K. The contents of the wall buffers are written out to disk at every transaction commit, so extremely large values are unlikely to provide any significant benefit. However, setting this value to at least a few megabytes can improve write performance on a busy server where many clients are committing at once. The auto-tuning selected by default setting of -1 should give reasonable results in most cases. That is true. I have yet to see a situation where I cared enough to change it, at least when testing. Leave it to -1, let it do what it needs to do. It's pretty smart that way. Wall writer delay. This is similar to the background writer, but now instead of talking about dirty pages, we are talking about the wall, the write-ahead log. Specifies how often the wall writer flushes wall. After flushing wall, it sleeps for wall writer delay milliseconds, unless woken up by an asynchronously committing transaction. If the last flushed happened less than wall writer delay milliseconds ago, and less than wall writer flush after bytes of wall have been produced since, then wall is only written to the operating system, the kernel cache, not flushed to disk. The default is 200 milliseconds. This feature does open a very small risk of data loss, but not corruption for uncommitted data. This is very similar to synchronous commit. You are trusting that you have reliable hardware, that you have a reliable software or operating system, and that you have a reliable database. If you're running anywhere near reasonable hardware on Linux LTS and Postgres, that is what you have. So make sure that you make use of this because it will be a performance benefit. Now, it's true. If you have uncommitted data, keep that in mind, what I just said, uncommitted data, the data that doesn't technically exist yet. You have not violated the D in ACID, and you crash, you may lose that data. But it's not going to change your consistency, it's not going to break foreign keys, it's not going to corrupt anything. It's like the transaction never happened. That's no different than the fact that you're running a web app and you hit X on Chrome in the middle of a process. Okay? Wall writer flush after. Specifies how often wall writer flushes wall. If the last flush happened less than wall writer delay milliseconds ago and less than wall writer flush after bytes of wall have been produced since, then wall is only written to the operating system, not flushed to disk. If wall writer flush after is set to 0, then wall data is flushed immediately. The default is 1 megabyte. Very similar to the back-end process flush afters. It's basically a cache within a cache, just so you're not writing unnecessary data, because we're only talking about a very small amount of data, right? These two are actually one of my favorite settings. Commit delay. Commit delay adds a time delay measured in microseconds before a wall flush is initiated. This can improve group commit throughput by allowing a larger number of transactions to commit via a single wall flush. If the system load is high enough that additional transactions become ready to commit within the given interval, however, it is, within the given interval. However, it also increases latency by up to commit delay microseconds for each wall flush. Because the delay is just wasted if no other transactions become ready to commit, a delay is only performed if at least commit siblings Other transactions are active when a flush is about to be initiated. Also, no delays are performed if fsync is disabled, which you will never do because fsync is not to be touched and will be left on. The default commit delay is 0, no delay. Only super users can change this setting. Beginning in 9.3, the first process that becomes ready to flush waits for the configured interval, while subsequent processes wait only until the leader completes the flush operation. While it may appear to be redundant with wall writer delay, the wall writer actions take place after a commit. The commit delay is used before the commit to potentially group together or group commit siblings together, and thus you see commit siblings. The short version of this is if you have a lot of highly concurrent small transactions that are being committed, basically you have a busy server, Postgres will say, hey, I've got these 5. Let's do these 5 at once. Instead of 1, 2, 3, 4, 5, we got a bucket and we write it out. So if you configure it correctly and you can test it, benchmark it, you can actually see quite a bit of benefit. Checkpoints. Checkpoints now are something that I don't even really think we need to have. They made sense in the older versions, but now with BG Writer and with the wall log and everything else you can do, it's almost kind of a legacy thing, but it is still something you definitely want to configure. A checkpoint is a point in the transaction log sequence at which all data files have been updated to reflect the information in the log. All data files would be flushed to disk. Basically, it's a consistency check. Everything, all the different changes, everything that's sitting around, it goes snapshot. Okay? The checkpoint command forces an immediate checkpoint when the command is issued without waiting for a regular checkpoint scheduled by the system. Checkpoint is not intended for use during normal operation, meaning just during your normal day, don't issue a checkpoint. You do need it when you're about to do a backup, like a base backup for replication. Checkpoints are issued, things like that. But during normal operation, it's not needed. The default checkpoint settings are almost always too conservative. I would say they are always too conservative, not almost. Using the same test but with 16 terminals connections as before, consider the below. My checkpoint, the default, 5 minutes. Max wall size, 1 gig. TPS, 740 transactions per second. Okay? All I do is change it to 10 minutes, increase max wall size to 2 gig, and I've got over a 10% improvement. Personally, I would set that to a minimum of 1 hour and have your max wall size be somewhere around 5 gig. Because you really only need this checkpoint, A, because it makes you feel better, and that's valid, don't get me wrong, and B, when you're running base backups, binary full backups, and that'll do it by itself. Checkpoint timeout. The amount of time to wait before a checkpoint is issued, the default is 5 minutes and almost certainly too low. The maximum is 1 day. Checkpoint is used to ensure that all data has been written to disk. That's true, except that we already have 17 other parameters that are making sure that all my data is written to disk. Not to mention I have the wall log, which I can recover from just in case some of my data hasn't been written to the page files. So my recommendation is at least 1 hour. Possibly more. Max wall size. Maximum size of wall files, PGX log, that's now in the newer versions, it's PG_wall, W-A-L, that are allowed before a checkpoint is issued by Postgres. This is a soft limit. Wall size can exceed max wall size under special circumstances, like under heavy load, a failing archive command, or a high wall keep segment setting. If you are running a modern version of Linux, specifically 9.6 or above, do not use wall keep segments. Use replication slots. That's what they're for. Okay? The default is 1 gig. Increasing this parameter can increase the amount of time needed for crash recovery. Wall keep segments is now a deprecated parameter, only supported for backwards compatibility. That's true. Now you use max wall size or replication slots. Min wall size. As long as wall disk usage stays below this setting, old wall files are always recycled for future use at a checkpoint rather than removed. This can be used to ensure that enough wall space is reserved to handle spikes in wall usage. For example, we're running large batch jobs or bulk loading. The default is 80 megabyte. Okay, checkpoint completion target. This is another one of my pet peeves. Okay, the point of checkpoint completion target is to smooth checkpoints. Because if you think about it, if you're under heavy load and all of a sudden you issue a checkpoint and the entire system wants to go on disk, okay, that can be very, very expensive based on how much data you have running. The problem is, this specifies the target of checkpoint completion as a fraction of total time between checkpoints. The default is 0.5. To determine, here's the key, to determine how often a checkpoint will occur with this setting, use the following formula. Checkpoint timeout divided by checkpoint completion target. Think about that for a second. What is the default checkpoint timeout? 5 minutes. We already know that's going to kill your performance, period. But now we have this other parameter that says actually checkpoint timeout is not 5 minutes, it's 2.5. So by default, Postgres will checkpoint every 2.5 minutes. Right? Set it to 0.9, increase your checkpoint timeout as much as it makes you feel comfortable, walk away, have a cup of coffee, and laugh as everybody else is moving slow, and you are not. Checkpoint flush after. Whenever more than checkpoint flush after bytes have been written while performing a checkpoint, attempt to force the OS to issue these writes to underlying storage. We've already talked about all these flush after settings. Doing so will limit the amount of dirty data in the kernel page's cache, reducing the likelihood of stalls when an fsync is issued at the end of a checkpoint. This is a very real thing. There are times when you are pushing so much data that your kernel cache just gets overloaded. And Linux is trying to push out all the data. And you will see spikes in your, if you're running something like sysstat with IO stat, you will see spikes where your IO just jumps. You have no idea why. It doesn't make sense. And there's a good chance it's because your kernel cache is getting overrun and there's not enough data being written out to keep it full or empty enough. Checkpoint warning. This is one of my favorite settings because it makes no sense as to why it's set the way it is. If you are checkpointing more than this value, Postgres will warn in the log. The default is 30 seconds, and it is too low. So I want you to think about something. It's going to tell me, yo, DBA, you're checkpointing more than every 30 seconds. Well, shouldn't it actually tell me anytime I checkpoint more than checkpoint timeout divided by checkpoint completion target? Why are you telling me at 30 seconds? At 30 seconds, I'm already screwed. My alarms are going off everywhere. On-call people are being paged. My boss is yelling at me. The website's stalled. Right? Your world has ended at this point. Right? You're crawling under your desk looking for a manhole cover to escape. So set this to at least the calculation of checkpoint timeout divided by checkpoint completion target. Because it's going to tell you, hey, your checkpoint timeout and checkpoint completion target are wrong versus an arbitrary, oh, by the way, every 30 seconds you're checkpointing. Okay, planner method configuration. The following parameters are useful for determining why certain query plans are choosing different paths. They should not normally be turned off in the configuration file. Instead, use set to test your query. For example, set enable bitmap scan to off, explain, analyze verbose cost query. So where this is really useful, I find, I mean, they're all useful, but the ones that are really useful are things like enable index scan, enable index only scan, enable nested loop. Because what you can do is you can run a query and you're like, this doesn't make sense. It's so slow. I got everything indexed right. What's wrong? Okay? So for example, set enable seek scan to off. You're forcing an index scan, and yet the planner still doesn't use the index. Why? The index is probably bloated out too far in that the planner says, I don't care what you say, it's better to use seek scan, or your index is corrupted and you don't know it. That type of thing. If you're an SQL developer and you really get into this stuff and you're looking for micro optimizations, it's also useful. Every once in a while you'll run into a query where, depending on where you have a particular clause in the query, it will choose a different plan. Now, that doesn't happen so much anymore. Our query planner has actually gotten pretty good. But every once in a while it still does, and what you can do is, for example, if you're getting a merge join and you shouldn't be, or you're pretty sure you shouldn't be, you can turn that off and see if the new plan, which doesn't use a merge join, is faster. And then you can start diagnosing where, who, what, when, where, you know, why it's doing what it's doing. Okay. Planner cost constants. Planner cost constants are largely arbitrary and used to determine a value of retrieving or operating on a tuple, a row, based on the type of access the planner has chosen, index, sequential, blah, blah, blah. You can set these options in the PostgreSQL.conf, but you may also test them in a similar fashion to planner method configuration by using set within the session. A really good, so for example, seek page cost. This is the cost of sequentially fetching rows from the disk. Generally speaking, the default is fine. It's absolutely true. And the reason this is weird is because these are arbitrary. So if you set them all to this, like if you were to take them all and multiply them by 4, every single one of them you multiply them by 4, you're going to get the same thing as what you had before, because they're all interrelated. So seek page cost is set to 1. Random page cost, the cost of a random fetch across or access to the tuple from the disk. The default is 4, meaning that the planner will prefer sequential scans in many queries, if not most queries. If you are running RAID 10 or SSDs, you can usually set this to 1. Realistically, if you're running anything of any moderate I/O performance, make random page cost and seek page cost the same. I don't care if it's 4, 4, 1, 1, 2, 2, it doesn't matter. Make them the same. Because then the planner is going to choose, based on equality, which one makes more sense. And especially when you're dealing with, say, 20,000 IOPS EBS volumes or SSDs, it really doesn't matter if it's a seek scan or a random fetch. Okay? And by setting it to the same, it is going to allow you, the planner to say, yeah, we're not worried about an index scan. Now you think to yourself, well, of course I want an index scan. Well, no, you may not. And here's where. Let's say you have 1,000 rows. It may actually be faster just to scan all 1,000 rows than to go all the way to the index, transverse the tree of a B tree, find all your leaf pointers, and then go back to the heap to find what rows to return. Now the question is, how much faster? That depends. But I have actually seen situations where you're literally talking about a 20 millisecond query versus a 22 millisecond query. At which point, why do you care? Okay? CPU tuple cost sets the planner estimate of the cost of processing each row during a query. The reason you need all of these is because CPUs used to be slow. They're not anymore. So it's actually not expensive, generally speaking, for a CPU to process a tuple. I would leave this one alone. Index tuple cost sets the planner estimate of cost of processing each index entry during an index scan. Operator cost, greater than, less than, greater, equal than, that kind of thing, sets the planner estimate of the cost of processing each operator or function executed during a query. Parallel setup cost sets the planner's estimate of the cost of launching parallel worker processes. Keep in mind that a lot of the worker processes are pre-launched, so it can actually be a very low value. Sets the planner's estimate of the cost of parallel tuple cost. Sets the planner's estimate of the cost of transferring one tuple from parallel worker process to another process. When does that happen? It's when one process gets the data it needs to be able to hand to another process for merging or whatever to deliver to the client. Min parallel relation size sets the minimum size of relations to be considered for parallel scan. I don't remember what the default is. All of these are literally, you got to test them. There's no good parameter. It's not like shared buffers where I can say to you, here's a general grouping of ideas of how to correctly set shared buffers. These are different than that. What I can tell you is, like I said, if you've got any reasonable I/O, the first two, seek page and random page, make them the same. I have found that CPU tuple and CPU index cost on newer boxes is fine. Just leave it alone. Operator cost, however, can be changed. Sometimes it needs to be increased based on how intensive your operator usage is. Right? If you're processing lots and lots and lots and lots of queries over greater than, less than, or any other operator, that can increase the cost to the planner, and it might make more sense for the planner to be a little more aggressive or less aggressive depending on what you're doing. Short of it is, you got to test. Everybody loves testing. Unit tests are great. All right. Effective cache size. This is one of the misunderstood settings. Effective cache size is not a memory allocation. If you set this to 16 gig, it is not 16 gig of data being set aside for some cache. Okay? What this is a hint to the planner to determine how much data may be in active cache. Remember that PG buffer cache query? Active cache. The calculation of effective cache size is percentage of cached plus shared buffers equals effective cache size, where percentage depends on the workload, but usually the higher the better. If set too high, it can be a performance hit, as the system will prefer index scans over sequential scans. But again, remember what we're dealing with here. All of these recommendations, everything you read in these docs, are all based on the idea that we are all running 4 7200 or 10K SAS drives in a RAID 10 with a small battery-backed cache. Generally speaking, nobody's doing that anymore. They're either on a cloud, in which case you don't even have to worry about it because they've got all kinds of weird stuff going on, or you're on-prem and you've got SSDs, again, not really a difference in cost. So the goal here is not to worry so much about whether or not you're going to hit an index scan, but to make sure you actually will hit the index scan. That's what effective cache size effectively does, is it says, I know that this data is cached, and therefore not sequential scanning is going to be faster. And remember, it is not a memory allocation. Okay. Genetic query optimizer. Absolutely, what I'm about to say is absolutely true. Discussion of this feature is outside the scope of this training. Generally speaking, the defaults work best. I'm saying two things here. One, I have no idea what this thing does. I've never understood it. I don't want to understand it. I know it works. I'm happy it works. Okay, it's kind of like my microwave. right? I know when I push it 1 minute, 30 seconds, my coffee will be reheated and I'm good to go. I don't care how it did it. That is what this is with Postgres. If you want to look into it, if you're one of these people that really likes to stretch their brain in ways that it's already a solved problem, but maybe it's not a solved problem, so I'm going to stretch my brain to make it a not solved problem that's already solved, go for it. Dig into the code. Awesome. But that's what it is. The one thing, I can't remember what the setting is, but there is a setting in here that it has to do with the number of joins. And if you look under the heading Genetic Query Optimizer, it says something like min joins for activity or something, and it says basically if you have more than 12 joins, that's when this guy will kick in. So if you are averaging large queries, where not 12 joins is a lot of joins. If you're doing 20, 30, 40 query or joins, you might want to look into that. But this is not something that, honestly, it's just not my scope. All right, other planner options. This is actually really important. Default statistics target. This is the amount of statistics to... Okay. So I got a story. I did a presentation at the University of Northern Arizona. That would be in Arizona. That's in the United States. It's an interesting state, very dry. It has this small thing called the Grand Canyon in it. And I was at the ACM. I don't know if you guys know what the ACM is, but in the States, that's kind of our computer science club. And it's applied, I don't even remember what it stands for anymore because nobody joins it. But it's an old school computer science club, basically. Most of the universities have it. And I was on a stage very similar to this, where I had two screens. They were larger, but there were two screens. And I was talking to a bunch of students. All of them were about sophomores, so say year 2 in college. And I was talking about open source in general. What is open source? Why is it good? Because, of course, this was back in the day when Sun Microsystems and Microsoft, the two of them owned universities, right? They didn't teach you how to do computer science. They teach you how to do Java or .NET. Now, it's not that that's bad because they are producing people that can generate work, which is good. But they don't necessarily generate people that can think, and that's bad. So I'm having this long... training going on about open source, all the cool things about open source, all the things you can do, what Perl is, what Python is, what Postgres is, what Java, everything. And there's this kid sitting right about where this guy is sitting right here. I'm going to point at you, sorry. And his phone rings. And I'm bringing this up because this is not the first time a phone has rang in this training. And I don't mind, sometimes people's phones ring, you forget to turn it off. That's not a big deal. This kid answered the phone, and he didn't answer the phone like, hey, I'm busy, I gotta get back to you. He full on was like, yo, what's going on, man? Now, I don't know if you noticed, but I don't mind pointing people out. And I stopped, and I'm like, really? Really, right now, you're gonna do this right now. And everyone's looking at him, and he's like getting offended. He's like, how dare you interrupt my call? And in the same situation, I'm like, you realize we're being recorded right here, right? You realize in front of all your peers and your professors who are in the back of this room, you are answering the phone while someone is giving a presentation. Don't do that. It's rude. Anyway, so the amount of statistics to be stored by analyzed for use by the query planner. It is an arbitrary value used to determine the volume, the size, the number, of statistics collected on a relation. And really, it's not even the relation. It can be also on a column, not the relation as a whole. The larger the value, the longer analyze takes, but generally the better the plan. The value can be set per column on a relation to store a higher amount of statistics on a selective basis. The simplest way to know if you need to increase the value is to review and explain analyze plan. If we look here, look in the bold. This might be kind of hard to see, but the last line of this plan here, it says, here's my estimated rows, 52. and here's my actual rows, 3,600. That right there is telling you, under no uncertain terms, your default statistic target is too low, period. And you're going to get bad plans. Bad plans mean bad performance. Okay? The parameter can be tested per session. For example, set default statistics target to 200, analyze the relation, explain, analyze, verbose, blah, 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 and then you'll see the row estimates line up. Now, this is not a big deal on most databases, but there are databases where you're analyzing so much data that the statistics are just, you're going to end up with a huge amount of data in PG statistic. So what you can do instead is on, I would say on select, don't do it across the board, but on select relations where you know you are querying all the time a particular where clause, where x equals whatever. You can increase the statistics on x, on that column only, and then run analyze. So you don't have to bulk out your PG statistic table with a bunch of unnecessary statistics. As a general rule, don't do that. I wouldn't recommend it as a general rule, but there are definitely times when you're talking about, especially larger data sets, where you might want to do that with just one column within a particular table. Constraint exclusion, a setting of on, off, or partition. The default is partition and the recommended setting. The use of constraint exclusion allows a planner, via check constraints as well as planning, to determine which relations within a partitioned set contain the data the query is looking for. Now, what does that mean? It means that you can set up a partition set, let's say over 100 partitions, and you can say this partition, based on this check constraint, only has this data. And that way, when you query the partition set, the planner will only look in the partition that matches the check constraints for that data, instead of traversing the entire partition set. That being said, nowadays the planner is good enough to where you usually don't need the check constraint because the planner knows already. So then the check constraint becomes a situation where you are restraining the data because you want to make sure only that data is in that partition, versus necessarily needing the planner to figure that out. I'm not sure how it applies with the newest versions of partition. In fact, I do. In version 10 and 11 of partitioning, now that we have actual partitioning, this is probably a legacy setting. From collapse limit, the planner will merge subqueries into upper queries if the resulting from list would have no more than this many items. Smaller values reduce planning time but might yield inferior query plans. The default is 8. This is that setting with the genetic query optimizer thing we were talking about. Setting this value to GQ threshold or more may trigger the use of GQ planner, resulting in non-optimal plans. All right. Is it 1:30 that we break out of here? Okay, so we're not going to get through this. We're not going to get all the way through this. It's already 1:15. So if we want to have a Q&A session, we probably want to do that now, right? Okay. Do people have questions? Or should I just continue? Okay, we do have some questions. So let's get that started.
Исключен? Скажите, пожалуйста, вот, допустим, у нас есть какая-то инсталляция.
Please tell me, just for instance, there is installation.
I don't speak Russian. Beautiful language, but I have no idea what you just said. I mean, you might have just asked me to marry.
let's imagine the following situation. We have a server, there's an instance of a database, and we actually allocated a lot of memory to this database. Everything is working fine. But how do we know that we didn't give it too much memory? How can we actually, it's like, 78 gigabytes. Is it too much or too less? Probably 16 gigs would be enough. How do we know what amount of memory is enough?
Okay, so there's two responses to this. First response is there is never too much memory. I mean, it's just that simple. I say that in the very beginning. However, I get where you're coming from. What you're asking is, and I assume you're running something like VMware, where you're in a shared environment, where you have a finite number of resources over multiple volumes or multiple images. The best way that I could recommend testing is you monitor the underlying OS for the memory that is being utilized. Because what will happen, a really easy way to see this is if you look at, where is it? Let's see. That's really small. Hold on a second. Well, I don't see it here, but if you use free, the Linux free command, for example, it will tell you how much free memory it has. And if you monitor that under your highest production loads, just use Zabbix or Nagios or whatever, Grafana with Prometheus, whatever, it will tell you, you'll be able to see when that drops and where the threshold is of the drop. And that will tell you, oh, I really do have 4 gig, for example, more than I need to have. Now, there is a huge assumption here. The assumption is that you're appropriately configured in the first place, right? Because Postgres is limited in what it will use for a lot of things. And so if you want to know how much is too much, you first have to make sure that you're at least appropriately configured. If you're appropriately configured, then you can watch that free setting, how much free memory is available, and then I would do it over time. Don't do it over a week, but do it over like a month of full production use, because that will take into account growth and everything else, and then you can reduce resource utilization based on that. Anybody else?
And so I would like to ask, if I'm running Postgres on Windows system, and I see that the accused to the disk all the time, how can I reduce it with Postgres tools, not to change the disks?
Well, first, it would be to install Linux and then run it on that. Thank you. But no, where you're going to want to look is things like shared buffers and your checkpoint timeout, because what's likely happening is that those aren't set high enough, and so server processes and checkpoints are happening too often, and it's grinding your disk. So increase your shared buffers, check for queries that may be overrunning work mem, and then also check, for example, checkpoint timeout, and that your BG writer is appropriately configured. And that way you're not going to get that bursty stuff where it's just grinding all of your disks. But the true answer is just install Linux.
Yeah, thank you very much.
Hi. My question is regarding full page writes, the parameter you're talking about. Yeah, okay. Well, regarding the wall files, right? I'm tending to turn it off because...
Don't do that.
Well, I explain, okay? Because it's greatly increased my performance and the wall size and everything. So I'm always thinking, what's going to happen if I crash my server, and what's going to be my consequences after everything goes bad?
Full page writes is not quite as dangerous as fsync, right? Fsync is dangerous, period. Full page writes is more of a, there is a chance you will get corruption if you crash, but you may not. Fsync is you will get corruption if you crash. There's no way for me to say it'll be on the 5th crash or it will be on no crashes or whatever. But if you turn it off and you don't have, if you're not running like on a 0 or something like that, there is a definite chance that at some point, if you crash, you might get corruption. Now, here's the catch. Run point-in-time recovery. Make sure you're shipping logs off to another server. So, okay, yeah, you crashed. That sucks. Oh, you got some corruption. That sucks too. No big deal. I am going to restore to the exact point in time. I'm going to recover to the exact point in time to right before the crash, and we're good to go.
Okay.
So that's how I would handle that.
Okay. Another thing, you were talking about fsync and how not to turn it off. But for me, when I see the setting, it's like a big red button just push on me. Why is it there in the first place?
Well, because back in the day, in the older versions of Postgres, it was a huge performance benefit. Huge. Well, yes, but there's a point where you have to ask yourself, do I want to go fast or do I want to go fast right into the wall? And when I say wall, I'm talking about the brick wall, okay? I would rather take the performance hit that I do. And it's not as bad as it used to be, right? So fsync itself, if you have a battery back controller or you have with cache, or you're running SSDs, your performance benefit is pretty nominal, if anything. But if you don't have that, you're right. Turning fsync off is great, but you're guaranteed data corruption if you are running transactions and you crash with it turned off. Why is it there? I asked once, right? I went on the list. I'm like, guys, really, nobody, Grant McAllister. If you guys don't know who Grant McAllister is, he is the guy that architected Amazon RDS and Aurora, right? He is the man. And he likes to come to my talks because I'm smarter than him. Not really. But he does. He actually does like to come to my talks. We get along really well. And I actually brought it up once at PostgresConf in 2015. And I said exactly what you said. I'm like, well, it's such a performance benefit. Why, you probably shouldn't turn it off, but maybe under certain circumstances. And he interrupted my presentation, and he's like, no, leave it on. Okay, so you're right. It is a big red button, and we like to push things. We're like, ooh, I wonder what this is going to do. It's going to hurt. Just leave it alone.
Hello, my name is Vasily Xentil, today company. So my question is about the synchronous and asynchronous replication. The main point is that I have 2 data centers and multi-master state. So I want to know, is there any possible way to be ensured that all the data migrates from one master to another except the synchronous replication? Because asynchronous is not so safe and synchronous is too slow.
You kind of answered your own question. So no, I mean the best thing you could. So one, if you have 2 data centers, you're going to have the network latency issue, right? So there's that problem. The other problem is you're right. Async. The problem with async is you might lose data. 2, the data you won't necessarily lose it, but it'll be inconsistent and therefore cause conflict. Those types of things. My honest recommendation: don't run multi-master. Okay, usually, now, you might be the exception. There's 230 people in this room. You might be the one exception. Usually people that run multi-master do not understand the problem. Okay, I'm not saying that to be rude. It's just the truth. I often hear people, I want to run multi-master because it's that big red button, and it's a sexy red button. Multi-master, the idea that no matter where I insert my data, it just magically works. There's a reason Oracle Rack cost $1 million, right? There are some weird solutions you can do if you want. For example, in the newer versions, you can use logical replication to merge result sets. So it's not actually multi-master. It's you write to this one and you write to this one and then they replicate to each other, which is not really multi-master. It's kind of a different thing. And so you could look into that. But the problem with sync is if you do synchronous, especially synchronous multi-master over a WAN, basically over the, over a network interconnect that's not local, you're going to kill your performance. There's no way around that. We just haven't reached that level yet. Now, that being said, look into like Yugabyte. Okay? Yugabyte is a company, they're in the Bay, in California. It's open source. What they did, they're actually the founders. Who here knows what Cassandra is? Okay, we all know what Cassandra is? Okay, Cassandra is kind of a MongoDB competitor. Well, these guys said, well, I've kind of reached the limit of Cassandra. So instead, they built it on top of Postgres. And they have geographically distributed, replicated nodes where you just point and it figures it out. So I would look at Yugabyte. That's an option. Another option, which is similar, but it's going to feel weird, is Cockroach. So Cockroach, what they did is they said, we don't want to deal with having to have all new drivers, all new syntax, that type of stuff. So they put a layer of Postgres on top of a different database. And it's also geographically distributed, and it's also open source. You're welcome. Well, there's one more. The other one is ProtoDB. Now, this is interesting because it's actually an app layer over data sources, and it's what Facebook uses. Okay? So those would be three. You're not going to get it with Postgres proper, but something similar, you should be able to pull it off. You're welcome. Anybody else? Cool. Thank you for your time.